Welcome to a video analyzing an amazing technical fabrication. Today we will together dissect the principles of making a hydroelectric generator. The project starts with a thick, walled industrial PVC pipe. The technician proceeds to measure and accurately mark the initial dimensions. Using a handheld angle grinder, the craftsman decisively cuts off a section of the PVC pipe. Right after that, a longitudinal cut along the pipe's axis is carefully made. He then repeats this basic mechanical operation on another section of the pipe. PVC plastic is a thermoplastic polymer, easily changing state when sufficient heat is applied. The mastery of operating the high-speed cutter produces very sharp, clean cuts. Adhering to dimensional tolerances is a vital principle for mechanical components. The thermal processing step begins by evenly heating the PVC pipe over a gas stove flame. Thermal energy temporarily breaks the polymer bonds, making the material flexible and soft. As soon as it reaches the ideal plastic state, it is manually pried open and flattened. The craftsman uses pliers to trim the deformed edges to create a flat sheet blank. The surface of the sheet blank is mechanically roughened with a piece of sandpaper to create micro grooves, increasing the contact area for mechanical adhesion. Specialized solvent cement for PVC pipes is applied thickly and distributed evenly. The solvent reacts chemically, micro-melting the surfaces of the two plastic sheets. When pressed tightly together, the solvent evaporates, creating an extremely solid structural bond. This composite material provides solid mechanical durability for the partition. Continuing, a soft measuring tape is used to precisely measure the outer circumference of a standard gas cylinder. This metal cylinder serves as a shaping mandrel for the turbine casing. The blank fabrication process is repeated. Another measured section of PVC pipe is cut off, preparing for the stretching and flattening process under the application of heat. The heating technique requires patience. Uneven heating causes localized shrinkage. Residual stress inside the material will warp the resulting machine casing. Under the protection of heat-resistant gloves, the plastic blank is easily flattened out. The structural transformation phase, from a cylindrical shape to a flat surface, has been successfully completed. Using a tri-square and metal calipers, precise alignment marks are drawn on the surface. These dimensions are calculated based on the gas cylinder's circumference and the splicing margin. Removing the excess material with an angle grinder happens incredibly fast. This blank will become the enclosing wall for the hydraulic impeller chamber. Cleaning the scratched surface is a non-negotiable process to prevent water leakage. The PVC strip is heated again to restore its plastic state. For shaping, the operating temperature is quite high. The technician must bend and shape it quickly. Heat dissipation occurs very rapidly upon contact with the metal mass. Shaping by wrapping the blank strip around the gas cylinder's body, taking advantage of the perfect curvature of the mold. This manual thermoforming. The process utilizes the residual heat to press and form the ring shape. The craftsman carefully marks it before using superglue to secure the two overlapping ends. Ending the ring formation cycle, we have a sturdy geometric structure. The heavy objects used for compression, like the inverter and battery, are removed from the base plate. The glue layer has cured, creating a flat, rigid, and load-bearing partition. The newly created ring is used as a template to sketch out a circle equivalent to the required area. The table saw makes continuous tangent cuts to perfectly extract the circle. Through successive tangent cuts, the excess material is completely removed. The saw blade, spinning at high speed, creates a round blank ready for assembly. The precision of the circle depends on the operational skills and cutting angle control. A perfect circle will ensure the concentricity of the generator system later. The process of peeling away small sections one by one helps minimize the risk of cracking the PVC material. The craftsman uses the edge of the saw blade to smooth out the remaining rough edges. The round frame and bottom panel are ready to be joined together. Cyanoacrylate 502 adhesive is used, thanks to its ultra-fast curing and strong adhesion. The 502 glue spreads into the gaps via capillary action, creating a perfectly watertight seal. Next, determining the geometric center is a crucial step to prevent vibration. He rotates the round panel evenly on the wooden block, using a marker to draw intersecting lines. The intersection of these diagonal lines is the precise axis center of the turbine system. A small center hole is pre-drilled to guide larger drill bits. The metal flange is placed at the center position as a reference for marking. Using a metal drill bit, the holes for the locating screws are drilled through the plastic casing. The excess burrs are immediately trimmed off with a utility knife to create a flat surface. Preventing water leakage from the turbine chamber into the motor housing is a major technical challenge. A piece of recycled rubber from an inner tube is cut out to serve as a sealing gasket. The elasticity of the rubber will fill every tiny gap between the flange and the casing. The rubber gasket is test-fitted into position, and scissors are used to cut off excess material. The craftsman presses down hard with his finger to punch out the holes, matching the screw positions on the rubber membrane. And here is the core component: a 1000W brushless generator motor. The motor's rotor shaft is passed through the center hole, which has been pre-lined with the waterproof rubber gasket. The generator is quite heavy, requiring the mounting points to be extremely sturdy. A hand drill continues to bore holes for the motor mount, piercing through the PVC partition. The flying shavings from the cut show that the drill bit is very sharp, and the applied pressure is incredibly precise. The process of test fitting and drilling one hole at a time helps completely eliminate mechanical assembly errors. The motor is now placed face down in preparation for tightening the bolts and nuts. Inside the water chamber, a socket wrench is used to securely tighten the mounting bolts. The tightening force must be even, so the rubber gasket deforms uniformly, optimizing water tightness. Moving on to fabricating the hydraulic impeller, he uses a metal hole saw. The hole saw creates small round plastic discs from the leftover PVC material itself. The rotation speed of the drill, combined with the alloy teeth, creates smooth friction cuts. Multiple small round discs are made to be assembled into a thick cylinder that can withstand torsional forces smoothly. Specialized PVC pipe cement is used again to bond the thin plastic discs together. They are stacked to form the drive shaft, transmitting kinetic energy from the impeller to the generator shaft. The contact surfaces are evenly coated with a solvent layer. They are carefully stacked on top of each other into a solid block and placed under a red hydraulic jack for compression. Tons of static force help squeeze out air bubbles, creating a solid density. The drill press ensures the center hole remains absolutely perpendicular, avoiding the phenomenon of eccentricity, which causes vibrations that can destroy the motor bearings. A table saw is used to cut deep cross-shaped grooves into the cylinder. These are the mounting slots for the blades of the hydro turbine. The central block has now become a complete mounting hub, ready to receive the blades. To harness energy. Returning to the table saw, a flat PVC sheet is cut into rectangles, whose dimensions must be completely identical to eliminate any imbalance. The measuring process is verified again with a tape measure, confirming the meticulousness. Any deviation in weight at high speeds will cause damage. Assembling each blade into the central cross-shaped grooves. The mechanical friction within the narrow slots temporarily holds the blades in place. A mechanical hammer is used to tap evenly, pressing the blades tightly against the hub. This turbine assembly will operate on the impulse kinetic energy principle. The turbine is carefully installed onto the threaded shaft of the generator, and the lock nut is tightened with a socket wrench to firmly lock the drive system. Bevel cutting the plastic water supply pipes using a handheld angle grinder. The beveled end optimizes the impact direction of the water jet onto the blades. placing the beveled pipes against the casing of the turbine chamber to mark the drilling positions for the two symmetrical intake pipes, creating strong and balanced thrust. A degrinder is used to cut oval openings. Along the edges, they are filed precisely to fit perfectly around the pipe body. Two intake pipes cross diagonally through the chamber wall. The turbine fits extremely tightly. This angled position is the core point, directing the water flow to hit the blades directly. Applying superglue permanently secures the pipes to the casing. Impacting simultaneously from both sides doubles the torque. Finally, the entire impeller is completely positioned inside the hydraulic chamber. Now, just closing. The bottom cover tightly finishes the compressor casing. The original round flange is fitted to the bottom, sealing the system. Pressure sealant is applied around the rim, ensuring there are no leaks. Taking the finished product to the field, it is tested right by the dirt ditch, where a discharge pipe of water provides an excellent source of potential energy. The builder begins cutting and assembling the rod, right-angle elbows to guide the flow. This branch system evenly distributes pressure to the two ports. The manifold system is prepared and connected very meticulously, using T-junctions, and right-angle elbows evenly divides the hydrodynamic pressure. The four main water supply pipes are connected directly to the flow splitter. High-energy water is forced to split into two symmetrical streams. The technician quickly cleans the equipment surface. Having completed the installation, the turbine unit is placed firmly on the soft ground by the canal bank. An AC household electric fan is brought out as a test load, directly connecting the fan's power cord to the generator's output. Twisting the copper core wires must ensure a good contact area. Alternating current from the stator will be instantly transmitted to the fan motor. Stepping firmly to push the exhaust pipe deep into the soft mud helps eliminate the reaction force, preventing vibration when the water pressure is high. And wonderfully, the Senko fan blades immediately start spinning extremely powerfully. The micro hydroelectric system operates perfectly, based on the natural flow's potential energy. A close-up shot shows the rotor of the 1000W generator, spinning rapidly at high speed. The continuously changing magnetic field through the copper coils is inducing a large current. The household electric fan operates extremely smoothly, reaching its designed rated speed. This proves that the output, voltage, and frequency of the generator are incredibly stable. Looking at the discharge water flow pouring out into the dry ditch with white foam, one can see the conversion efficiency of the impeller turbine chamber's kinetic energy is very impressive. The technician places his hand directly on the metal casing in closing to feel and thereby evaluate exactly the mechanical vibration and heat generated while under load. A thumbs up confirms the brilliant success and efficiency of the entire project. The video closes with an open countryside natural landscape that is peaceful and tranquil,